After you've mastered how to write electron dot formulas on a piece of paper, which is a flat sheet and we're kind of limited to the two-dimensional world, you have to really start thinking about how molecules really look in a three-dimensional world, because that's the world that molecules actually live in. The simplest model for modeling this type of behavior, and it actually works rather well, is called the valence shell electron pair repulsion theory. And the name's probably scarier than it actually is as far as it works. We often just call it the VSEPR theory, and then we kind of just say it all together, Vesper theory. So you'll hear me say Vesper theory from now on when I mean the previous. So the way it works, and the name kind of gives it away, is you take your electron dot formula and you simply count electron regions around the central atom, and you realize that each of those regions is a negatively charged region, and so it's going to repulse all the other negatively charged regions, and they're going to try to get away from each other. They can't completely get away though, because the nucleus of the central atom is holding them in. So what they do is they try to get away from each other, but they're still held by the central atom. This leads to distinct molecular shapes. And the easiest one is two regions. If you only have one atom on one side and one on the other, and they try to get away from each other, you get a fairly linear type molecule. And so that's the first one. Two regions gives you linear shape. The bond angle is 180. Stepping up to the next one, three regions. You count the regions around the central, there's three. If three regions try to get away from each other, you basically get a nice kind of pie shape. It's like taking a pie and cutting it into perfect thirds. So you get a 120-degree angle all the way around for those three regions. Both of those regions are still planar. They still look just fine on a sheet of paper. It's when you get to four regions that you have to go to the third dimension. You have to go three-dimensional. And what this gets you is a shape that we call a tetrahedron or tetrahedral geometry. It's four regions around a central, all perfectly symmetric. And if you take a look and spin the molecule around and look at it, every region is equivalent. And the bond angles are now down to 109.5 degrees. That's a tetrahedral geometry. So as you can see, the bond angles are getting smaller because we're bringing in more regions. We started at 180 for linear, 120 for trigonal planar. Now we're down to 109.5 for tetrahedral. So that really sums up most of what we will use, especially in organic chemistry. And that is at the heart of Vesper theory.
The arrangements of the electron domains about a central atom are determined by the electrostatic repulsions between like charges. The electron domains stay as far apart from one another as possible, while at the same time they are held by their attraction for the central atom. When there are two electron domains about a central atom, they are located 180 degrees apart to minimize repulsions. Three electron domains about the central atom take up positions in a plane separated by 120 degrees. Four electron domains form a tetrahedral arrangement about the central atom.